Welcome everyone. So this is our 82nd live stream geometry. We have 3 people here with us from all around the world. And today I'm going to do more problems that I found on the Art of Problem Solving forum from the user Live to Love 212. So I believe either he or she is from Vietnam. And they have some fantastic problems that they posted about. Some of them they created themselves. Some of them they replied to other people's comments. So for everyone watching, if you'd like to join us in the future, feel free to email me at mgreenv801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So I see we have one more person joining us, and I will start on the first problem. So I think the first 3 problems are a little bit easier, maybe, and then the last 3 are a little bit harder. So if these are too easy, we could always move on to the last 3, but I don't think any of these will be that easy. So we will see. So you have a triangle ABC, and BE and CF are the altitudes. H is the orthocenter. All right. Yeah, the very last problem has 3 different mixed to linear end circles, so I don't think that will be too easy, but never know. Okay, there's no point D in this problem. So this is E and F, and they intersect at H, and EF cuts BC at T. Okay, so we already have we could create a harmonic conjugation here, right? If we draw the altitude from A. So I'm going to do that because that's often useful. So that's T, but we're going to have a G later. Well, okay, we'll just call that I for now. P is a projection of O. I think O is the circumcenter. I think they forgot to add it to the problem. So we draw the symmedian. So I will do it by drawing the 2 tangents at B and C. Okay. I'm going to clean this up in just a second. So it looks nicer. I think there's something special about the projection of A on, the projection of the circumcenter onto the symmedian. I think it bisects the symmedian chord, if I'm remembering correctly.
It has a lot of special properties. It is called the Dumpty point, I think.
The Dumpty point, yeah. So let me draw that. So that's going to be P. So it's the midpoint of this chord, and it's the harmonic conjugate of the Humpty point, which is, I think that's video 5 on my channel, and a couple of other things. So I'm going to draw this point. OP cuts BC at point G. So let me delete this point G, and then the other point G, I think, will show up when I create it. Okay. And so this should be G, and then reflect G about T, and you get point L. So this should be L, and we want to show that PL is perpendicular to PH. It's kind of interesting. Okay, so we have a lot of information here. I'm going to make it look nicer, of course, because there's too many lines. But yeah, it's not that complicated of a diagram, actually. It just looks messy right now, but yeah, I feel like once I clean it up, it won't be so messy anymore. Okay, so, all right, that should be good. We have this, this, this and this, and EF cuts BC at T, and then this is the orthocenter. So yeah, this is really, yeah, the whole diagram. So we want to show PL is perpendicular to PH. P is the midpoint of AK. That's kind of a well-known fact. And that's actually not hard to prove because we have angle OPJ is OBJ is OCJ, and they're all 90 degrees. So this is a cyclic quadrilateral right here. And I mean, just the fact that this is perpendicular means it has to be the midpoint of AK, actually. So that's not, this doesn't even have to be a symmedian for that to be true. Okay.
Could you please repeat it one more time? I didn't get the first one.
Yeah, sure. So since OP is perpendicular to this, because P is a projection of O onto this median, then AP has to equal PK by symmetry.
Yes.
And then also OPJ is 90 degrees, and OBJ is 90 because this is tangent, and OCJ is 90. So this is a cyclic quadrilateral with diameter O.
Okay, I understand. Thanks.
You're welcome. So yeah, how do we use that GT equals TL? Well, let's see if AO and L are collinear. I don't think so, but it's worth checking. No, they're not collinear.
It is quite obvious that the GA is the tangent to ABC.
GA is tangent to the circle. And that's because this is a harmonic quadrilateral. Well, but yeah, GA and GK, I guess, would both have to be tangent, right? Yeah, so ABKC is harmonic, and so the tangents at A and K have to concur at a point, and then that point will lie on OP. So yeah, those are both tangent. Okay. This almost feels like some kind of spiral similarity. We want to show PL is perpendicular to PH. Are there any similar triangles we can use? I mean, I could draw the midpoint of BC. And then these have to be collinear, OD and J. So yeah, how do we use that GT equals TL? So that means that let's see, you think PAH is similar to PGL. Interesting. I can go check that. Yes. So I'll label the midpoint of AH. We can call that M. It's a nice name. I didn't have to work too hard there. Okay. So yeah, in triangle PGL, T is the midpoint of GL, and then PAH, M is the midpoint of AH. So maybe we could show PGT is similar to PAM. So yeah, MP is parallel to HK. Oh, really? Okay, so it's equivalent to the problem. Okay. So if PAH is similar to, yeah, because that would mean APG, PAG is similar to PHL. So yeah, but so using spiral similarities, yeah, it's equivalent. So yeah, for Simon, because I know you're learning more about spiral similarities. So Hakan, so basically we want to show that triangle PHL is similar to triangle PAG. That would solve the problem because we know PAG is a right triangle. So if they were similar, then PHL would be a right triangle. So that would mean PL is perpendicular to PH. But that would be a spiral similarity, right? Taking triangle PAG to PHL. So if that is a spiral similarity, then basically there's a theorem, and it's not hard to prove, that there would have to be another spiral similarity, that PAH would have to be similar to PGL. So if we can prove that also, that would also solve the problem. Okay.
Yeah, I understand.
And we know that PM is parallel to HK because M is the midpoint of AH and P is the midpoint of AK. So we could try to show that they're similar to AHK. We could try to show that AHK is similar to PGT. Maybe we can use ratios. Yeah. So can we show that? Yeah, so we know that angle PAI is equal to angle PGT. So we know that one of the angles is equal in those triangles. So I'm looking at KAH and PGT. We know that one of the angles is equal. Can we show, yeah, maybe use ratios. So yeah, let's see how we might do that. So I'm going to draw in, we know that this is a cyclic quadrilateral. But I'm going to hide that just for now. So we have AHK and PGT. Yeah, how can we get ratios? So yeah, it seems is PG, like PG seems like it might be able to be calculated because basically OP times OG is OA squared. So yeah, maybe that could help calculate it. I don't know. Yeah, how do we get GT though? I think that's the tricky thing. Yeah, calculating GT seems like the hardest part. So maybe there's another way we can do this. Maybe we could try to find, maybe we could try to find the angle that EF. Well, actually, I think this should be doable. We want to show the angle that EF makes with BC. Oh, actually, never mind. Because we're working with point P. So yeah, I don't know if it helps to draw this circle right here. It should pass through the midpoints of A, B, and BC, A, B, and AC. So if these are perpendicular, then I wonder if like AB is perpendicular. So like, let's see. What do we get if we draw the perpendicular from O to AD? Is that like the, let me see if there's something special about this point right here. Is AL perpendicular to ET? It almost looks like it. So yeah, I think it might be. I probably could have just drawn the perpendicular line instead, but oh, I don't think so. It's 92.3 degrees, almost. Yeah, not quite. But I think AO is perpendicular to ET, I'm pretty sure. Yeah. The 9-point circle. That's an interesting idea. So yeah, that passes through the two midpoints. And then we have ANPOQ as cyclic. And these circles are tangent, this circle and this circle. But yeah, how do we get, we want to show GPT is similar to AHK. Are any kind of ratios? Like, yeah, with GT, that's the hard part, getting GT. So we could also draw the perpendicular from H to AD. That would be the Humpty point. I don't know if that would help.
It may help since that point is also the reflection of K over BC.
Oh, good point. All right, so.
And also that point is the isogonal conjugate of P.
Yeah. The Humpty and Dumpty points are orthogonal conjugates. So I'm going to draw that point. Called R because I don't know. So HR is perpendicular to AD and BHRC is cyclic. That's like video 4 on my channel. And yeah, these are reflections. And then also we have another cyclic quadrilateral, AFHR E is, so yeah, we have a lot of information here. Are T, R, and H collinear? I think that, yeah, T, R, and H are also collinear. That's also in my video 4 on my channel. So, yeah, we have a lot of information here. Okay. I wonder if we can, let's see. I wonder what the angle bisector of, let's see. Is P, no, I don't think that's true. I was gonna say maybe PHL is similar to PGK. Let me check that. Oops. So PLH. No, that looks smaller than this angle. Oh, I think they are similar. PLH and PGK. That's interesting. But it's not a spiral similarity. Well, it would be a spiral similarity PHL to PGA. So maybe we could try that. So if PHL is similar to PGA, then PLG, oh, but we said that before. We want to show PLG is similar to PHA. Yeah. Okay. Just one in a circle. But now that we have more information, maybe it won't be as hard to get GT. I'm not sure. So is there any, does T lie on any circle? I don't know. Well, what about, let's see. So what if I drew this circle? So the circle with diameter GL. And then, yeah, I wonder if there's anything special about that. I'm not sure if there is. Yeah, maybe not. So we have GK squared is GB times GC. And yeah, I wonder if G is in harmonic conjugation. Like what point is G in harmonic conjugation with on BC?
The intersection of AK and BC.
Ah, I did not realize that. Okay. So G, B, S, and C are in harmonic conjugation. Yeah, because if you project through A, then you'd get A, B, C, K. So, okay, that looks like it might be useful. And D is the midpoint of BC. So what does that mean? Is there like, I forget how the multiplication works, like something squared is DC squared DS times DG. I think that's true, right? DC squared or DB squared is DS times DG. Is that true?
Yeah, that is true.
Okay. So yeah, we might be able to calculate PG from that. Or maybe, so I haven't used this trick in a long time, but like if you have one harmonic, like if you have 4 rays that are harmonic and you have another 4 rays that are harmonic and 3 of them are perpendicular, then the 4th one has to be perpendicular. So maybe we could use that too. Because we know a G, a B, a K, and a C are harmonic. And what else? We also know that, yeah, Kg, Kb, Ka, Kc is harmonic. So yeah, can we use any of that?
Oh, I think that the problem is equivalent to showing that TP is perpendicular to HK.
Oh, really?
Yeah. How I got to that is we would apply polar transform. And okay, so let's step back a bit. We want to show that AMP and GPT are similar.
Yeah.
So because M is midpoint of AH and P is midpoint of AK, we want to show that AHK is similar to GPT.
Yeah.
Then,
and yeah, if we show that HK is perpendicular to PT, then that means all 3 of the sides are perpendicular to the 3 sides of the other one. So they have to be similar.
I didn't get to that in that way, but okay.
Yeah.
So basically, I was a couple of days ago, I was reading about polar duality.
Okay.
And then I thought about applying polar transform. So angle GPT, we want that to be AKH.
Yeah.
And that is the angle between the lines AK and HK.
Yes.
And when you apply the polar, you take the poles of those two lines, we would have a pole of AK is G, and pole of HK is some point, but O and that point would be perpendicular to HK.
Okay.
And then we would basically want to show that the GPT, that angle is GO and that point, the pole of HK.
Okay. So we'd want to find the pole of HK.
Yeah, you can draw it. It's a bit not that easy to follow everything in head.
But yeah, I think once you mention that, I think it's simple enough. Like if you look at triangle GPT and AHK, we know that GT is perpendicular to AH, and then we know that GP is perpendicular to AK. So if we could show that PT is perpendicular to HK, then all the corresponding sides are perpendicular, right? So they have to be similar.
That makes sense.
Yeah, I think that's maybe
it's
an
simple,
easier.
yeah.
But yeah, polar duality is interesting. Like, yeah, I feel like I should read more about it. But I think I kind of see what you're saying. Like you look at what point is the polar of HK, and then from there it would be some work, but you could prove it that way. Okay, so yeah, that seems like maybe a little easier, showing that PT is perpendicular to HK.
Now we can actually get rid of G. I think.
We can hide a bunch of stuff. We just want to show that, yeah, PT is perpendicular to HK, which is much easier. Or it seems easier. I don't know, yeah, so H is not the orthocenter PTK. But so, okay, so TR is perpendicular to AB. Yeah, I'm trying to make an orthocenter, although I don't know if it's that easy. Yeah, we'd have to intersect TP with AB. And I don't know if that's really anything special. Let's see. Yeah, I don't think there's anything special about that point. How do I draw a good diagram here? I think that's good enough. So TP, we want to show it's perpendicular to HK.
Oh, now we should take the midpoint of HA. Now we want to show TP and that midpoint is 90 degrees.
TP in the midpoint of HA.
Yeah.
So that's M. Okay.
Yeah. TPM should be 90. And that looks like we can interpret in cyclic quads.
Okay, yeah, because that would mean TPIM is cyclic. Well, that just means P is the midpoint of EF, which is obvious because AK is isogonal to the median and EF is anti-parallel to BC. So does that solve the problem? So yeah, I can prove angle TPM is 90 degrees.
Could you say again why?
Yeah, so showing that angle TPM is 90, it's the same as showing that P is the midpoint of EF.
But P doesn't lie on EF.
Oh, I got confused. You're right. Okay. Yeah, that's a good point. So if we took the midpoint of EF, which is that intersection point right here, then we know that MU is perpendicular to UT. And we want to show that PM is perpendicular to PT. So we want to show MPUT is cyclic, I think, right? And I would also pass through I. Yeah, so we want to show, we know that MUIT is cyclic, and we want to show that P lies on that. So can we show like MPUI is cyclic? That looks like probably power of a point from A. We want to show that AM times AI is AP times AU. That seems like it shouldn't be that hard, right?
Yeah, that is doable, 100%.
Yeah. Okay. Yeah. So I think that would solve the problem.
Yeah.
So because AM times AI is AH times AI over 2. And AP times AU is AK times AU over 2. So then we want to show UHIK is cyclic. And is that obvious?
Yeah, you can angle trace, for example, that UKCE is cyclic.
UKCE is cyclic.
Yeah, UKC is ABC, that angle.
Yeah.
And that's it.
But I want to show UHIK is cyclic. Does it follow?
Then you do powerful point again.
Okay.
Since HICE is cyclic.
Okay. All right. So that's a nice solution with a lot of stuff. I'm sure we don't need everything in a diagram. I don't think we need, do we need the 9-point circle?
No, and we don't need the point R.
We don't need point R.
Also point D.
I don't think we need this, right?
Yeah.
Yeah.
Point S. We don't need anything.
All right. So I will unhide.
Also point D and
Point D we don't need.
yeah.
All right. Let me make it so L lies on the segment BC. So yeah, we want to see P and we want to see U. So I'll try to make a diagram where we can see both those. Do we need the midpoints of AB and AC? I don't think we need it. Let's see. Oops. Okay, so I think this is really all we need right here, right?
We don't need point D.
We don't need D. We don't need this. Okay. Okay, so we want to show, I'm trying to remember what we just did, but we want to show HK is perpendicular to PT. That's kind of the first step. And we did that. Oh, okay, so we start with U. And okay, so first I'll say label the points as shown. I'm not going to write out the definition of all of them. It's hard to make P and U farther away. So let's see how I can do that. I think that looks fun. Okay. Shown. Let me make it serif. U is the mid, so AK is a symmedian and EF is anti-parallel to BC. That means U is the midpoint of EF. And then once we have that, then so we have angle MUT is equal to angle MIT equals 90. So that's cyclic. All right. And then we want to show P lies on that. So we want to show MPUI cyclic. But we have MH times MI, or we want to show AH times AI is AU times AK, but AH times AI is AE times AC, because IHEC is cyclic. So so we have IHEC is cyclic by right angles. I'm too lazy to write out the equality. So AH times AI is AE times AC, and we could show that's if KUEC is cyclic by an angle chase. So that's just because angle AUE, if we drew the midpoint here, well, or yeah, we could just say angle AEU is angle AEF, which is angle ABC, which is angle AKC. So yeah. Which is angle ABC, which is angle AKC. And that means that KUEC is cyclic. Okay. So we have AH times AI is equal to is it AE times AC? Yeah, AE times AC, which is AU times AK. And that means that 2AM times AI is equal to AU times 2AP, which implies AM times AI is AU times AP, which means that MP UH, or sorry, what are the points? AM times, oh, this should be AM times AH. Sorry, I got confused. No, AH is 2AM. It's AU times AP, which means that MPUIT is cyclic. Because we already knew MUIT is cyclic, now we know P lies on it. So angle PLH, yeah, so what did we get from there? Then we knew, angle MPT is 90, right? And what did we do after that? Okay, so we wanted to show HK is, okay, we wanted to show HK is perpendicular to PT, but that's the same as showing MP is perpendicular to PT. So HK is parallel to MP by midpoints. And that means that HK is perpendicular to PT. Okay, and then we have those three triangles. So we have AHK and PGT, and the sides are mutually perpendicular. So sides are mutually perpendicular, and that means the triangles are similar. So AHK, and that implies AMP is similar to PGT. And I'll say by a spiral similarity at P. And that means that PM, so if AMP is similar to PGT, then that means that that means that PAH is similar to PGL. And that implies triangle PAG is similar to PHL. By the spiral similarity. And so that then implies that, sorry, PAG is similar to PHL. And from there we get PL is perpendicular to PH. All right. This was a fun one. So yeah, I like this problem a lot. So let me fix, this dot looks a little weird. AE, oh, I need the C. There we go. All right, so I'm going to move on to the next problem. Okay, so we have a triangle with orthocenter H, and O is the circumcenter. Whoops. So this should be O, and H should be the orthocenter. And P is an arbitrary point on BC. So H, P is a random point on arc BC. Sorry, this should be posted. Here's P. Pick your favorite point and reflect it over BC. So it's P prime. We also know the reflection of H over BC lies on the circle. So we draw the circumcircle of OPP prime. So this is an isosceles triangle, and it intersects AP at G. Let's see if I can, that looks a little better. So this, yeah, let me do this. So yeah, this is an isosceles trapezoid here, and so it's also going to be cyclic. I'll draw that in later. And this would be point G. And we want to show that the orthocenter of AGO lies on HP prime. Okay, let me close this. Let's see, I don't know if it's also worth drawing this circle or not. Maybe not. Yeah, I'm not going to draw that for now. Okay, so we want the circumcenter of AGO. I wonder if there's another way to do this. Like we could also let HP prime, so let's do this. Let's draw HP prime, and let's draw the perpendicular from G to A, or G to, so it's AGO. Okay, so let's draw AO in, and let's draw the perpendicular from G to AO. Does it meet on this circle? And not only that, does it meet? Okay, it meets on the circle, which is interesting. Can we prove that? So that, because if we show that, we want to show that D is the orthocenter of AGO, but first we could try to show that D lies on this circle. So we want to show DGPP prime is cyclic. All right, so I'm going to hide some stuff. Or we could redefine things so it's cyclic. But the way I define things, basically, I let AP, so basically I drop a perpendicular from G to AO, and I let it intersect HP prime at D, and then I want to show that DGP prime P is cyclic, which is kind of the same as saying that, well, actually, never mind. But yeah, that would be what I would want to prove.
So you, I think if we let D as the orthocenter, it is very easy to prove that it lies on OPP prime.
Okay, so define D to be the orthocenter.
Yeah.
Okay. All right, so let's do it that way.
Okay, so let me just think for a second.
Oh yeah, I hid this circle. I shouldn't have hid it. But so define D to be the orthocenter. Okay, so it's kind of tricky to, because like, yeah, it's like we can't assume that D lies on this circle. That's why I kind of try to define it the other way, but we could define it that way.
I think intersect DO with AP.
Okay. Are they perpendicular?
Yeah, I mean, that's the orthocenter.
Yeah, they'd have to be. Yeah, you're right.
Okay, then FD times FO is equal to FG times FA.
FG times FA.
Yeah,
yeah,
because
reflect. Yeah.
And FA is FP. So by power of a point, DGOP is cyclic.
Cyclic. Okay. And okay.
Also intersect the DA. Just draw in the segment DA.
Okay. Yeah, it looks like it might pass through the intersection of those, right?
Yeah.
Yeah. Let's see. Why is that? Okay, so we should hide this basically, because we don't know that yet, right? Okay. Interesting. So yeah, we could like, maybe it might be easier to define this point, and then we want to show DI and A are collinear by an angle chase. So angle DI, we could try to show angle DIO plus angle OIA is 180. So angle OIA is angle OAI.
Yeah. Angle chase does it.
An angle
OIA
chase
plus OIA plus actually I use that they're cleaner, prove that they're cleaner.
Okay. So DIO is DGO. And so we want to show DGO plus IAO is 180. And DGO is 180 minus DAO. So yeah, I'm kind of just going in circles now. Let's see. So we want to show H. What if we reflected D over BC? Because these points, I mean, like these points are the reflections over BC. So maybe if we reflect D over BC, we'll get something interesting. So that's going to lie on the circle by symmetry. And can we say anything about that point? Maybe not. But is there another point here? Point J. Yeah, no, that doesn't do much. I don't think so.
I think we can prove that DI are collinear, but we should define I as intersection of DA and OPP prime.
Okay, so I could hide this circle. Then I want to show, I'm going to add it back in just a second, but that I could show I lies on this circle is what you're saying.
Yes.
Okay.
So we want to show that OA is equal to OI.
Okay.
But that should be clear since angle DIO is DGO. And that is the 180 minus DAO.
Okay.
So basically, OIA is isosceles.
So yeah, that's actually, yeah, pretty simple proof. That's a good point.
Also, I don't know if you noticed, but BHP prime C is cyclic.
BHP prime C. Oh, by reflection. Yeah. I did not realize that. So yeah, maybe this is like radical axis theorem. Okay. So yeah, let's see if we could use the radical axis theorem. So I'm not sure if it'll really work. Just trying out stuff. In fact, I'm not so sure it will. Doesn't look like it. Yeah, I'd really like to reflect D over BC, but yeah, it just doesn't look like there's anything special about that. I guess what we could do, we could we could let H prime P meet this at D prime, and we could try to show that D prime and D are reflections over BC. So yeah, maybe could I extend PP prime to meet ABC again? Yes. So that's J. Oops. Sorry. All right, so looks like we solved it. Okay, so we have VP prime P is angle DIP, which is ACP, which is AJP. In fact, we could skip the ACP. We could just say DIP is AJP. And that's HP prime P. Oh, because AH is equal to JP prime. That's okay. So that is really nice. All right, so I'm going to start typing that up. So we know that this is a parallelogram because basically AH prime PJ is an isosceles trapezoid, and H prime P prime P is an isosceles trapezoid, which means that that is a parallelogram. So, okay, so I'll say, okay. So I'll say, yeah, so G we've defined in the problem. So I'll say let D be the orthocenter of AGO. And let AD intersect OPP prime at I. Equal I. And then I'll just say label the rest of the points as shown. Okay. Yeah, I don't think we need H. Whoops, that's not a LaTeX. Okay, so first we want to show DIOP is cyclic, and that's not that hard because, as Stefan said, angle well, no, first we want to show I lies on the same circle as the rest of those points, but that's not hard because angle OID or angle OIA is 180 minus angle OID, which so OIA is 180 minus OID, which okay, wait, what did I do after that? I know. Okay, so 180 minus OGD, which is OAD. So that means that triangle OIA is isosceles. Or I'll just say even simpler. So OI equals OA implies I lies on the circle ABPC. Okay. And then we have AH prime PJ is an isosceles trapezoid, and HH prime PP prime is also. So AH prime PJ is an isosceles trapezoid. So is HH prime PP prime. And that those two together mean that AH prime PJ is a parallelogram. And then once we have that, then let me try to make this then we do the angle chase that Hakan put, and then that solves the problem. And we don't even need this one, although we could if we wanted. So DH and P prime are collinear. And that means that the orthocenter of GEO lies on HP prime. All right, that's another good problem. So the last three are a little harder. This is the second one. So we could do one easier first. Yeah, let's just finish this up, and then we will check the last three. So we have a triangle ABC. A P and Q are arbitrary points on BC, so that AP equals AQ. All right. So I'm going to do it like this. This should be P and that should be Q. The circumcircle of APQ intersects the sides at E and F. E, F. Okay, and then we draw the circumcenters of BPE and CFP. Okay. And we just want to show that O1, O2 passes through A, or A lies on O1, O2. Seems like it can't be that hard, right? So I don't know if we'll solve it super fast or if it's harder than it looks, but it doesn't feel that hard. Let's see, how do I make these circles? I can't make one smaller without making the other bigger. So let's see, but if I think that looks okay. Let's see, I wonder if QA and this, no, because by symmetry that they wouldn't be collinear. Okay. I want to make O1, O2 look less parallel to BC. Maybe that looks a little better. see. Yeah, the diagram is never going to be perfect, but yeah, I don't want to make it look like they lie on either circle, and I don't want to make it look parallel to BC. So I think that's good enough. Something like that. Okay. So maybe we could show the distance from A to BC is a certain weighted average of the distance from O1 to BC and O2 to BC. I don't know if that's the best way, but like we could draw the midpoints of PB and PC, and then the midpoint of PQ. But yeah, I'm not sure. Let me think about that for a little bit. So angle AFP is equal to angle AEQ because arc AP is equal to arc AQ. So that's probably going to be used somewhere because angle AFP, yeah, AFP is equal to AEQ. So I think BF, well, let's think about this. So AFP, I think, is equal to APB. I think so. So I think BF times BA is BP squared. Well, no, that's not, because that's not true by power of a point. So AFP, because AFP is AQC, which is APB. So they should be similar, right? Yeah, so AP squared is AF times AB. So BFEC is cyclic, I think. Yeah. Okay. And you probably just wrote that. Yeah. So yeah, so BFEC is cyclic because AP squared is AF times AB and AQ squared is AE times AC. Okay. And maybe it'll help to draw the center of this. I don't know for sure. So O1D, yeah. So we have angle AFP is equal to angle AQC, right? Because AFPQ is cyclic. So AFP is AQC, and by symmetry, that's the same as angle APB, since AP is equal to AQ. So since AF, that would mean angle AFP is angle APB, and that would mean that triangle AFP is similar to triangle APB. And so that means that AP squared is AF times AB. All right. Okay, so we want to show O1, O2 passes through A.
This is quite obvious, I think, now by inversion.
Oh, really?
Yeah, since if we invert around A with power with radius AP,
Okay.
then F inverts to B and E inverts to C.
Okay.
Since AF times F AB is AP squared.
Yeah.
And now P stays the same, and then circle FPC.
This circle.
FPC inverts to BPE.
Okay, so these circles invert to each other.
Yeah, and well, that it is like a well-known thing that centers stay like linear when invert. Yeah.
That is a very simple problem. So yeah. All right, so that was a fast one. So the next three problems I think will be a little harder, but that is a nice use of inversion. So, so we have angle AFP is equal to angle AQC is equal to angle APB. Means that triangle AFP is similar to triangle APB, and that means that AP squared is equal to AF times AB. Let's check the chat. Yeah, that was a nice one. So where did I go wrong here? Oh, triangle. And then we have similarly AQ squared, which is equal to AP squared, is equal to AE times AC. Okay. And then, so from there, consider an inversion about A with radius AP equals AQ. And then that takes the circle BFE, that swaps the circles BFE and CFP, or that swaps the circles BPE and CQF. And you could just do that.
BPE and CTF.
Oh, sorry, BPE and CPF. Okay. So yeah, so does point Q just like go away?
It's just there for us to show AP squared is AF times AB.
Okay. So yeah, for some reason I thought the problem was symmetric with respect to P and Q, but it's not, because these are both for P. So yeah, you're right. And so that means the centers, yeah, I'll just, yeah, that means that O1, O2, and A are collinear. All right, very interesting. So yeah, a simple inversion solves it. All right. This one might be a little easier too.